Okay, so if we take this big program here, and what I've done is I've rewritten the program to show you sort of the precedence constraints that need to be in place and for the execution to proceed correctly. So for example, this instruction loads a value into R1, which is then used by the next instruction. So we clearly can't execute those two in parallel because the compare has to wait until the load finishes. And you can see the first couple of instructions have to be done sequentially. Branches actually are a separate challenge because they represent a point which changes potentially the path of execution, which would mean that these instructions down here might be executed or they might not. It depends on whether that branch is taken. If that branch is taken, we won't execute these instructions. So there's some opportunities from parallel. We can look and say, oh, look at those instructions down there. I can run them in parallel. But depending on the branch, I may or may not want to run them at all. And we'll talk a little bit about how to solve that problem in a second. Down in the lower part of the program, you can actually see that it's possible to put a lot of instructions in parallel. Now notice that not all of these, so here's two of the loads, here's a fourth load. So I actually have to scan pretty far down the program, for example, to find these three instructions that can be run in parallel. The first two were right next to each other, okay? But if you keep going down, you discover this load is in fact doesn't depend on any of the earlier instructions here. So it in fact could be done in parallel with the first two loads. So in general, to get good instruction level parallelism, there's this notion of looking pretty far ahead of the program because you may actually have to go to sort of a new calculation entirely to find one that's independent of the earlier instructions. So it's sort of interesting to sort of look at this and you say, wow, but this is pretty good. Here we're executing 3 instructions in parallel, or 2, or 3. Here's another 3 down here. So these all represent opportunities where, in fact, instead of taking all of these cycles, we might be able to do this program in 6 cycles, assuming we could execute up to 3 instructions at a time. And that's noticeably shorter than the entire loop here. And as I say, Intel has put a lot of engineers on this job. One thing that's interesting to notice, though, I mean, we talk about the loop structure of programs as being sort of one of the key things that allows us to execute programs well. One of the neat things to notice, in fact, is that often iterations of a loop are, in fact, independent of one another. Often you're doing a bunch of things depending on the index, or if you're doing a bunch of operations in A sub I and B sub I and C sub I from 3 different arrays, and it's complicated, and there's not a lot of parallelism there for a particular I. When you go to the next I, all the operands now are completely independent of the first generation, of the first time through the loop. So in fact, this notion of loop unrolling often gives us an opportunity to find lots of parallelism that could happen if we're willing to think of how to do 2 iterations of the loop at a time. So imagine that I had written this out instead of changing the index by 1, I actually put 2 copies of the loop code and then changed the index by 2, where the second copy uses the index plus 1. And I would discover that perhaps many more opportunities for instruction level parallelism. And in fact, things like the GNU C compiler spend some time doing these loop unrolling optimizations in the hopes of providing enough grist for your fancy processor to use the grist for the mill for it to be able to say, oh, look, I can my fancy 8-issue machine can suddenly has a lot more. I have a lot more different instructions that could potentially run in parallel because they're coming from different iterations of the loop. Okay. In general, it pays to, if you know that you're sort of playing this game, you can try to write your code in a way that unhooks unnecessary dependencies. But inevitably, there's going to be some dependencies. It's not like every calculation is independent of every other calculation in most programs. Typically, there's a set of things that you're doing where step 2 depends on the completion of step 1, and that gets in the way of instruction level parallelism. What would a piece of hardware look like? So this is a diagram that's not unlike the block diagram for a modern Intel processor. You can see, in fact, instead of having one ALU, in most Intel processors actually have multiple copies of these blocks. So here's an integer ALU, here's a floating point ALU. The load and store operations are handled by a separate unit. The branch operations are handled by a separate unit. And then each of the units has its own little queue of instructions that have been given for it to do. And so the way it works is we have this big instruction queue, and at this level, the processor is saying, could these two operations go in parallel? For example, if N1 doesn't depend on the instruction here, if this second instruction, does that depend on this instruction or not? If not, they could be issued in parallel. And so this is a so-called dual issue. It can issue up to 2 instructions at a time. The most modern processors can look at 8 different instructions, particularly if they're going to 8 different functional units. They can say, I can do these all at once. And you can imagine it takes a lot of transistors and logic gates to figure out whether 8 different instructions are all independent of one another. It's sort of like bypassing in spades. You know, you're looking, oh, is anybody using this destination register? No, okay, then we can go off and run in parallel. So these get issued to the different processors, and then each one of these functional units here, I should have said functional units, each one of these functional units takes its own sweet time. The integer functional unit may be in every cycle complete. The floating point may in fact take many cycles to complete. So eventually each of them, and the memory, access to the cache and the memory depends whether there's a miss in the cache. All of these different functional units produce results, perhaps not in the same order that the instructions were issued in. And so there's a reorder buffer that takes all the results and puts them all back into the correct order, and then makes sure it makes the changes to the register files appropriately. And then each of these guys, whatever instruction is about ready to start executing in it, says, oh, I need these operands. So there's a whole set of wires here on the operand buses that allow each functional unit to communicate to this giant register file that has umpteen read ports. You know, psst, give me register 2, I want register 5. And so there's an ability to ask for a lot of registers in parallel and actually get them all shipped to the different units. Complete with the forwarding pass, the bypass pass, it knows what's waiting to be written in the register file and says, oh, I haven't finished the writes yet, but here's the value you want. So the reorder buffer is keeping track of which registers are going to be written, and it waits until it gets so there's an add instruction, it knows it's going to write register 5, so there's an entry in here. Register 5 is going to be written by this instruction that's currently in functional unit 2, and so when the functional unit 2 finishes up, it can say, okay, I've got that answer, I can now go ahead and write it. Meanwhile, anybody who asks for register 2 can sort of be told, this functional unit is going to write it, but I can't give it to you yet. So all of the scoreboarding, keeping track of who's doing what and when gets pretty complicated, but if you spend enough transistors, there's the opportunity now to execute multiple instructions in parallel. Big, complicated beast. Now remember before I talked about branches and the fact that something branches, you don't know whether you're going to execute certain instructions or not. Speculative execution is just saying, well, I'm just going to go ahead and execute them anyway. When I find out what the branch does, either I'll keep the results or I'll throw them away. And actually a fair percentage of the work that your processors do is done speculatively. In other words, they're instructions that follow some branch, and the processor's just saying, well, I'm ready to run 5 instructions at a time, so I'll do both where the instructions following the branch and the instructions of where the branch is going to. I'll just execute both of those instruction streams, and in fact maybe get a lot of potential parallelism because they're coming from different parts of the program, and I'll just save whichever results turn out once I know what the branch does. So I think it's sort of neat. I mean, this is but you can imagine all the details you have to keep track of, and getting it right can be somewhat complicated.